Hello, everyone. So today we're going to continue the conversation about spatial data. So on Tuesday, I introduced the concept of spatial data models, so raster and vector data. And so now I'm going to talk a bit about spatial data more generally and what makes it special compared to other types of data. That's going to lead into a short conversation on spatial sampling. And I'll talk about a technique we can use to sort of exploit the special nature of spatial data to our advantage. And then I'm going to talk a bit about Lab 2. I'm going to introduce it and just give a bit of an explanation of what we're going to do. So last week when I introduced map projections, I started off talking about Tobler's first law of geography. It's really the only law of geography, but it comes up again and again and again. So I'm going to talk about it quite a bit this term. And essentially, again, everything is related to everything else, but things that are closer to each other are more related to each other than things that are farther away. So this makes sense intuitively, but it can be a bit of a stumbling block in GIS. This relates closely to something called spatial autocorrelation. This is when a value of one object is related to a value of another nearby object. So it's a way to sort of mathematically describe Tobler's law, if you will. If you know the value of one object, you can make a pretty reasonable guess at the value of another nearby object. It doesn't mean that they're the same, but you can assume they're probably similar. It also doesn't mean that the values of one object directly affect the values of another object, but it is possible. So one thing that's important to note here is that correlation does not imply causation. It merely means that there's a relationship between them. The relationship can be governed by something else, like a third object that determines the values of the other two. So we have different patterns of spatial autocorrelation, ranging from extreme negative to extreme positive autocorrelation. Extreme negative autocorrelation is pure dispersal, essentially, the most dispersed something could be. So envision a chessboard, for instance, where all the white and black squares are as dispersed on that board as they could be. Whereas extreme positive autocorrelation is intense clustering. Everything that is similar is grouped together, and everything that isn't like it is grouped somewhere else, right? So you can see down in the bottom right where we have all blue and then all white squares on separate sides. And between those, we have the versions of autocorrelation that we're more likely to actually encounter in the real world. We can have some sort of dispersed arrangement where things are negatively autocorrelated. We can have spatial independence. That's groupings are entirely random. Some are clustered, some are more dispersed. Or we can have spatial clustering where things tend to be more concentrated closer together, but again, it's not perfect. So spatial autocorrelation can be represented using a number between -1 and +1, where -1 indicates extremely negative autocorrelation, saying everything is evenly spread out. 0 indicates statistical independence, so again, just more or less random. And 1 indicates extreme positive autocorrelation. Everything is clustered very closely together. But spatial autocorrelation causes some problems when trying to do statistics because it violates one of the key assumptions of many statistical methods. Most statistical methods assume that there's no relationship between objects as a default, and then use that to test to see if objects or groups of data are statistically different, for instance. So by inherently being related based on space, we break the common assumption for statistics. So for this reason, there's actually a whole separate field of statistics dedicated to spatial statistics, where we have to work around and compensate for the flaws, or not flaws, but the issues caused by the relationship between variables due to their geography. Inferential statistical testing is common practice in many of the sciences, but these tests are generally speaking problematic for spatial data. Because spatial autocorrelation, the fact that similar things cluster near each other, violates the basic assumption that the samples we take are independent. They're not independent because they are close and related to each other. The idea of independence just simply can't be asserted between most samples that we work with in the geographic sciences. So the ideal condition for a scientific study would be to select data, to take samples of data that are far enough apart that it makes statistical independence more likely, but that's generally just not feasible when doing GIS work.